This conference will now be recorded.
Go ahead, Atan. You can go.
Okay, okay. Can you see my slides?
Yes.
Yes.
Okay, so I'm sorry that I'm not opening the camera, just that my experience, it caused my home internet to become extremely slow. So I think audio is preferred over video at this point. We're going to discuss today why we initiated this project, what we vision to achieve, to solve, what we see as challenges which require the entire industry collaboration. I think that OCP is a great place to incubate this, and personally, I'm very grateful for this home, and I think it's a huge opportunity to make a big leap in technology. We will try to vision the target of what we want to achieve. We don't have yet well-defined milestone and dates. We do have some before and after guidelines, and we will go over that. So I do like to thank my colleagues that incubate with me this great roadmap and idea. So thank you guys, and let's start. So we will start with why, and after why, the next question would be what is so different or unique than what existing today, and then we will map some challenges. I do feel that they will not be the last one. They are the one that we observed on the months or two that we are working on that, and some goals that we set for ourselves. And I did put a Q&A section at the end, but feel free to pop in and ask something. Although we may not answer at the moment, we can address this further on. Okay, so the first claim that we have is that the next generation data center does require time sync. And I'm not going to explain and protect this claim. I'm going to give you some teasing points that we came up with. And actually, Georgie from Facebook gonna discuss this, I think, next month. He will come up with some applications that we have been researched lately, and he will show it's really a huge benefit that comes with that service. So we do believe that TimeSync is a service that is kind of a must at the next data center. One thing that we observed, the messaging service, which is the heart of any micro segmentation, web hosting, cloud hosting, it has to preserve and promise the at most one message guarantee, and the TimeSync actually simplify this one. As I also have had as an architect, I didn't present myself. I'm an architect at Mellanox, now NVIDIA. And as a network architect, I can tell you that this is a very strong and hard to meet guarantee, especially in high rates. And TimeSync is something that can ace this. And Georgie will elaborate and emphasize some examples. The next thing that we observed is authentication tickets. Today, the scale is in minutes, which is amazing from my point of view. We believe that we can break it down into milliseconds, and this is like a very conservative assumption that we can do. Yeah, there was a question. Okay. The next thing is cache consistency. As you know, when in a distributed workload, same data exists in several nodes, and they are treated as cache. There are many applications managing this cache, and consistency is running on the internal web cloud hosting. And this cache consistency messaging is a huge workload. I mean, and it's also grow dramatically in peak times because it's grown non-linearly with the demand, and actually relaxing this service and offloading a huge part of it is a great benefit to the entire infrastructure. And what we observed is that there are a lot of papers talking about it, but precise clock can help you to synchronize the invalidation. So you don't need to wait for a specific data to come and make your cache dirty or to evacuate it. You don't need the extra communication that will trigger an invalidation event, which will take time. We can synchronize them, and the synchronization can be one that is doing it not all of the evacuation will happen at the same time, and this what will ease the networking load. I hope this is clear. I think this is one of the most reasonable tickets. Now comes the application part. All the first three were services part, but from application point of view, there are a lot of papers talking about the benefit from external consistency and coherent time axis. Actually, you can treat it as a service, by the way, but what we claim is that external consistency can make the service indistinguishable. I mean, which means that it's not dependent at the topology or the deployment, which means that you should not be affected when you scale up, which is a huge benefit and claim. It reduces a lot of testing, and it's allowed you to scale more easily. We have one quote that we find very nice: DC like a PC, notation from Google Spanner, famous paper from 2012. This paper, or one of its derivative, claiming to achieve 80x performance gain. That number by itself sounds unreasonable. We now believe this number is extremely realistic one after some investigation, and yet wait for George's lecture on that. Commit window, again, distributed databases. The commit window consistency will determine eventually the performance of your database. Actually, a distant node will now draw back the performance because the most distant node will determine the commit window as of today. With time sync, you are not the performance are not determined by the distant node. Yes, the distant node will perform slower, but it will not affect the other nodes. And of course, it brings a much higher availability, and also not fully decoupled, but a lot of decoupling is achieved from the network latency. And last but not least, because it's more visionary, on all the first one were down to earth, but we do see a trend in which the data center application wish to go all the way to the edge. You can think of it as the 5G era or the CDN era or whatever, and we do wish to allow that the same application will run on both facilities, and on the edge there is a time sync service. And once we equalize this and bring time sync service into the data center, it will be easier to migrate. I'm not saying it's going to be easy, but it's yet another step towards a smoothless migration. And we do believe that we will see few applications that the edge will be part of the service. But let's keep it for further down the road. So with respect to the edge, which time sync service is available, and we see PTP profiles in many domains like industrial and power and telco and broadcast, etc. Data center is a different point, and it's not different in the manner that PTP allow the trade-off between performance and price to be defined by the PTP profile. We believe that the data center require much different approach because of an entirely different trade-off pyramid. We believe that the first and most important thing that data center requires from this service is scalability. The fact that this is growing, I mean, there is not application that demands the growing rate. The growing rate is constant, and actually the growing rate is growing by itself regardless of a specific application performance, etc. And the entire DC is maintained much differently than the edge. The operation team that scaling up those facilities should be unaware to those services, because all the services in data center are scalable. And it relates to the PTP clock tree. It relates to performance. It relates to the timing restrictions. And what we want to achieve, first of all, it should be scalable. It means that when we add more pods, when we add more services, more nodes, the existing one should not be affected, and we assume that any addition will have the same performance as the previous one. So the service will be equalized in quality in all the pods. There are other topics that related to scalability that comes from the scalability of other services in the cloud, like virtualization, which means that it's not a simple packet. And yes, we know PTP doesn't define the packet layout, but virtualization is not yet another L4 protocol. It is a different complication with that, whether the PTP should be in the outer overlay network or in the inner one. An aspect like security. Most of the PTP deployment today run on trusted network, and it's not the case anymore, or at least we believe that we should also come up with a secured solution on that. And I think last but not least on this topic is the fact that we will not see greenfield deployments. We will not see a data center built from scratch. We will see that data center will grow and will add time sync service, and they will continue to maintain their old time sync service, which is NTP. And those services will have to coexist and depend on the business needs. We believe that the NTP will clear its place towards the PTP, and that of course depends on the progress in embracement and integration of the service in the application. But there will be few years or a decade, if I may. I don't want to frighten you, that those services will have to coexist together. So that's the basic, the fundamental requirement. The second one is reliability, and it means that the common infrastructure delivers some promises to the application that is hosting. For example, we stated here that it's okay to have an outage, or in our case, outage means accuracy loss. The lack of the service is is not the only thing. We're talking even about accuracy loss from if we decided that the service level is a few microseconds, then 1 millisecond is outage. What we want to state here is that we want to define a mechanism that will allow us to be as much as reliable as we can, which means that we must inform to the application on any event that the service is lost. Okay, it's okay to have an accuracy loss. It's extremely bad to have an accuracy loss without the application is being informed. It can cause silent data corruption, which is very bad. And this is, by the way, described very well in Google's final paper, and I believe that Georgie will also discuss this issue in his presentation. So we are talking about, first we are talking about the capability to observe and to promise such an reliability, but also since data center is maintained by automatic and operational tools, we understand that there is a need for monitoring tools, and any network transaction should be with or without, within or outside the error-bound budget. If we are promising a time service sync, we need to define per message running in the data center if this message is within the service, the time sync or not. And we don't familiar, or we don't know any well-known standard that promise that or deliver that. And not to mention that we need it in scale. So those are the fundamental one. Last, I mean, it's maybe it's I don't know if it's common knowledge or not, but any service that data center deliver is targeting to be offered as open source. This is becoming some kind of a well-known practice, relying on open source community. It's secured. It gives some confidence that the service will be continue to be maintained, etc. It allows the application to understand what it gets, and we believe that it should also be like that in this case.
Gautam?
Yes?
This is Rajiv. Quick question. Do we have this error-bound measurement service available as of today?
Not publicly. We know that there are some data centers that implemented it. We want to offer it as an open source, something that we will all accept as a community and maintain as a community. And we believe that once we will do that it will be adopted well.
All right. Okay. Thanks.
It's what described in Google papers, so I do assume that Google implemented it.
Oh, okay. Do we have access to the paper?
We can put the link to the paper. It's a public one.
Appreciate it.
Yes.
Thanks.
The name is Spanner, but we will publish a link. Thank you, Elad. Okay. We mentioned this. Data centers are, I mean, they are designed to be maintainable from my point of view, in the most professional way. It's divided into islands called pods. Pods can be pulled out for maintenance. Once in a while, there is a maintenance window. The people that maintain those pods should not be, or we should minimize their awareness to the services or to applications. There should be a management mechanism that allow to evacuate the application from the pods. And imagine that this pod is now part of an essential clock tree. Once you cut it off, it's not that you cut off some VMs or some guests that running on this pod. So this is one aspect. I'm talking about the entire aspect of maintenance So everything should be well observed. The service should be auto-discovered, etc. I bet you can think of other implication of that. And this is why we need the wide forum and the community to help us observe all the requirements. So what we intend to do is to come up with something. We will come with initial proposals, something we will come up with ask for requirements and problems to solve, and we will start defining them first before we come up with proposals. I think once we cleared all those three, scalability, reliability, and maintainability, now the service can be deployed on the data center, and now we want to make a good ROI. Okay, those are a must, and those are enablement. So the first thing after a service is available to the data center, it should be in the right cost performance point. And in this part we will have I assume we will have the proper definition in the PTP profile, which is different in other aspects as well. And Michelle is going to talk about it in the next meeting, I believe. But it is, I think it is very much well known that data center are super scalar comparing to edge nodes, which means that the cost return function is much different than any other thing. One thing we observed, but it's not the least, and it's not related to the fact that Gary is speaking right after me, is oscillators. So we believe that, well, first we believe that the oscillator selection will be different in data center than at the edge. The clock tree spread in much wider leaf count, and oscillator selection will effectively dramatically affect the cost. But it's not the only point. This is like a CapEx point. There is also an OpEx. Okay, any tools and monitoring that will allow us to observe and to serve this service at the data center and to maintain it will save us OpEx. Okay, the nature of those tools will determine how much the facility is spending on this service to make it viable. And OpEx is also important. And again, it's a different point than the telecom. And you might be surprised that the list of the important thing, it's yet important, but the list of the importance is the accuracy. And I'm saying it with some pain, because when we started this exploration, before we understand what's the problems that we need to solve, I personally thought that the accuracy is one of the most important thing, and the accuracy is important, and we should this what will allow us to achieve performance, etc. Only later on we understood all together, all the team, that without the basic of the pyramids, there is nothing to talk about the accuracy. Yes, the accuracy is important, but only after we achieve all those floor steps below. And accuracy will determine how much we will gain and accelerate in performance. By the way, from that reason, I do believe that we will not see any vendor locking. If we will standardize it, all those things, all those maintainability requirements, reliability, etc., we will see equipments that fulfill those requirements, and they will differ in accuracy, which will allow the cloud providers, the hyperscalers providers, to choose among several vendors. Again, those accuracy points should be well defined and can be several spots, but it is important. One thing that is different than the accuracy that PTP profiles discuss is the fact that the PTP profiles define accuracy in the clock level, in the node level. We believe that in the data center, it's almost meaningless to discuss clock level accuracy. What we want to make sure is the application level error bound achieved. And we will have our time. This will be a challenge. First of all, to define it, then to assure it, and then to maintain it. But this is the target. The service is targeting to promise an application level error bound rather than clock one. Of course, the clock will be there. There will be clock accuracy level, which will be much more demanding than the application, but eventually a service as a whole should deliver application level error bound. After saying all that, we try to rephrase the vision. We would like to, together with you, with this great community, with this great housing of OCP, to design, to make a blueprint that will allow fast, reliable, scalable, maintainable deployment of PTP in data center. Again, each one should be at the desired cost performance option that it wants, but this is what standards are all about. This is what consortium and community is all about. This is the only way to make sure that a good technology will find its way to the crowd. Otherwise, I think we are blocked. Okay, so this is like problems vision. The next step is what we intend to do. Questions so far?
Yeah, this is Lawrence Daly. Can I ask a couple questions?
Yeah, sure, go ahead.
So for most data centers up until this point in time, my impression was that at least in the core that they were depending primarily on NTP.
Right.
Is that true still at this point in time?
It is.
It's also my impression that the 1588 v2 Senki and PTP stuff, at least in the current usage in the telco market, is really geared towards the edge cell site gateways, and back into some of the aggregation routers in the telco network. And so certainly there's a lot of timing sync stuff going on there. But for the data center and stuff and the cloud, I'm new to this area and stuff. It's not my area of expertise. But are you guys have any comment about the company called TikTok Networks that seems to have a solution that's running at Azure and Google and looks like maybe soon at Amazon as well?
I'm not familiar with.
Again, the name, please, Lauren.
Called TikTok Networks, and in fact, their website is actually that, tiktoknetworks.com, and it looks like it's a monitoring and correction set of software that runs in these online.
So we will take a look into that, but one thing I can say with great amount of confidence that it's not deliver what we required, and I'm saying it because I'm the network architect at Mellanox, and we are the network provider for the cloud you mentioned, and
Okay.
we are not delivering this service.
One thing I may add, Lawrence, if there is anything that is aligned with what we are looking for, we're more than happy to work with them. Like, we're not trying to reinvent if anything exists. So like, I think next slide, Dotan will show you the lay of the land. Like, basically, we are welcoming anyone to come in. We're just trying to have everything aligned, more like a magnet, trying to put like all the magnetites like basically in one direction rather than reinventing anything here.
Right, and I totally understand that even what they may be doing may be related to, node by node management of time sync stuff, not application level management of time sync stuff. So,
and I think Georgie's on the call. Like he brought it up like a while ago about TikTok time. So we are looking into anyone who we can collaborate with. Like this is a inclusive, very inclusive effort. That's why we brought it up to OCP, to the cloud, to the crowd.
Yeah, and I'm appreciative of the fact that this got pulled into as a topic to discuss. Clearly, throughout the networks, cloud all the way out to the edge, this timing sync stuff is getting much more important for not just the hardware, but at the application level as well. So, fully supportive.
Thank you.
Thank you for the support. So what do we intend to do and what we don't? We don't intend to replace any of the standardization body. Actually, we even intend to empower them because we will rely on IEEE, PDP, and ITU. We will take a lot of ideas and problems that already been solved by the ITU. One example that I have in mind, several PTP profiles in the ITU defined noise tolerance. I mean, with respect to other PTP profiles that just define it as an accuracy, ITU defined, especially when it comes to 5G, noise tolerance, which means that if you have one node which is noisy, the other one, even down the road in the clock chain, should be robust to specific level of noise and do not allow this noise to propagate. So first, we do think that we will adapt this requirement. We do, however, believe that it should be defined not as a noise tolerance requirements per se, but maybe as an open source filter that we will maintain as a community. This is one observation that I had. And again, we are not replacing any of those. What we do intend to do is, of course, we want to come up with a data center profile for the PTP. This is something that Michelle will discuss. PTP profile will consider the length of the clock tree, the noise filter that I just mentioned, a measurement method. Okay, this is something that in some profile doesn't even mention. We do believe that there is a need for a common measurement method. Otherwise, you cannot state whether you are compliant or not. As well as, sorry, I was mixing between measurement and testing. So measurement is the way to observe that the level of service that you have. And this also needs to be defined because it has to be in scale. Currently, we are not familiar with any measurement method that comes with PTP and allow you to scale. And we will discuss this. We have some suggestions, but again, this is an open initiative, and we will collaborate and ask for feedback. And not to mention testing. So testing will allow you to qualify equipment, to qualify your service level, to do some tests from time to time, and those should be also well defined, as well as the testing suite by themselves. So this was with respect to the data center PTP profiles. Another thing that we believe should be defined is an open source grandmaster. Both the definition of what it does and also the architecture, because we do believe that it should be a commodity server with a commodity equipment running with open source software. And this hasn't been defined yet. So of course, there is an hardware that should be existing for that, and we want to define what hardware do we need, what would be the interface between this hardware and the commodity hardware, what would be the software stack that interface, etc. And it also implied that we will need more grandmaster than usual, because we want maintainability and scalable service. So I assume we will not settle for one grandmaster at the POP. We would like to come with an open source PTP stack. I'm familiar with a leading Linux initiative. I think some things are missing. We will try to contribute.
And we do plan to discuss that in one of the next meetings, right? This is
right.
Planned by Georgi to present in I think the next one.
I think the next lecture is by Michel about the PPP.
Oh, okay. The one after that, maybe.
Yeah, one after that. And I think, I also think Georgi will focus on the application targets and examples that I think the Grandmaster will come only after that. But let's see. We think, we suggest here, by the way, this is a much weaker statement than the previous one, that oscillator classes needs to be defined differently than the way they are defined today. Oscillator defined today by just with two parameters, wonder and jitter, and we already learned. Gary will discuss. I don't know if he will show you the same thing that he showed us, that those two parameters doesn't define oscillator, and they are not sufficient. And last but not least, I think this is the very most important thing, that all OCP will come up with a reference design for appliance server, and of course open and allow everyone to collaborate. And this, I believe, and I dream that will change the industry and allow this service to be deployed and to accelerate the performance of the application that we all enjoy day to day. I have one almost last slide about a sneak peek into some issues that we already observed. The clock tree in the data center is much different than anything that I encountered with. First of all, it's much more wide. Any boundary clock needs to serve thousands of leaves. It's by far something we need to address. And with respect to multi-host, which is also part of OCP, this is also scale, because each network node serves multiple nodes. So it's another factor. We should not neglect that as well, which means that how do we, if a PTP usually defined and maybe assisted by a NIC, and now a NIC is serving few hosts, we need to address this as well. Okay, the clock chain kind of splitting at the end while it's supposed to be converging. And again, it's not only wider, it's also longer.
Dotan,
yes.
Quick time check. Let's. Is this the last slide?
Yeah, it's the last one.
Perfect. Okay, so we'll move to the next session once you're done. Thank you.
Okay. The clock chain is not only wider, it's also longer, which means that if we will have a noise, the way it will propagate, it will determine a lot about the accuracy of the service. We need to make sure that the noise will not propagate, so the next error event will not happen during the propagation of the previous noise, etc. And I'm trying to make it fast. Sorry, Gary. Reliability means that we need to have some redundancy in the grandmaster level. I believe we haven't defined anything yet, and any other aspect that you can think of. So with that, I thank you. If you have any other question, we can just write them down or send them to me. I don't want to stall any more of your time and Gary's Gary's time.
So I have a question.
Sure.
So I recall in 2016 there was a paper in SIGCOMM about data center time protocol. Are we going to explore such a kind of protocols instead of trying to reinvent the wheel and do something new?
If you can send me the paper name, I can answer to the mailing list. I'm not familiar with the paper.
Okay, so
Or at least I don't remember.
yeah, it's a SIGCOMM paper from 2016 called Data Center Time Protocol. I will send the link to it.
Thank you,
you.
Hisham.
Yeah.
Hisham, as just a rule of thumb, we're open to anything. Like we again, this is a forum. We want absolutely, we don't want to reinvent the wheel. We will just like try to, I don't know, put the things like within what we are looking for, and completely collaborative, and any suggestion are basically appreciated. I think let's move on to Gary's presentation. Archana, can you make Gary as a presenter, please?
Gary, you're good.
Okay, thank you. One question before we get started. Am I supposed to be using an OCP template or my
It's
corporate
fine.
template?
It's fine. It's fine.
It's
open.
fine, yeah. No worries. It's completely open. Yep.
Okay, yeah, I wasn't quite sure. Okay.
We'll give you the material for next time, like for next
Okay, I
presentation.
wasn't sure of the ground rules, just being my second time here.
No,
So
don't
I'm
worry
gonna
about
go
it.
ahead and share my content. Can you see the screen?
Yes.
Yes.
All right. So this talk is a really introductory talk on the impact of oscillator noise on PTP time error. And I'm going to do the start and the end of the presentation. The majority of it's going to be by our Senior Manager of Customer Engineering, Nazar Jasinski. And I'll just let Nazar say a quick hello and also pronounce his last name correctly, because I'm sure I mispronounced it. Go ahead, Nazar. Nazar?
Can't hear you very well.
You're on mute.
He's not muted, but it's just, I think it's very silent.
Maybe.
Or something.
Yep. Okay, maybe Nazar,
we still can hear you.
his audio.
Oh yeah, looks like the laptop did not pick up my microphone.
Oh, great.
Okay.
Can you hear me now?
Yes. How do you
Yes.
pronounce your last name, Nazar?
Shinsky.
Shinsky. Okay, easier than I thought. All right, so let's go ahead and get started here. So as we know, PTP is becoming the de facto standard for synchronization across multiple industries, including 5G and data centers. And it requires a high quality oscillator for the best performance. And it's important when analyzing oscillators to look beyond the banner specification of the stability, because there's a lot more going on behind the scenes. So today we're going to take a look at a model to analyze the PTP time error, and we're going to look at particularly how the frequency variation changes with changes in temperature. We call that temperature sensitivity. And wander is another aspect of noise, and that's basically low frequency jitter. And then also aging of the oscillator plays a role. If you'd like holdover, otherwise its aging isn't as critical. So we're gonna go ahead and take a look at these noise processes, how they impact PTP time error. And then when we're done with that, we're gonna take a look at an architecture using a dual MEMS scenario that was really optimized for minimizing PTP time error, and we'll show you how that's done. So at this point, I'm gonna turn the slide over to Nazar. Okay, Nazar, you should be good to go.
Okay, yeah, it's the button just got enabled.
Yep,
Okay, it looks like it's on now. Okay, since we have limited time, I'll try to do this quickly. Maybe let's start from locating the where the oscillator actually is in the 58 system. Where is it physically present? So PTP is just a protocol. PTP packets travel Ethernet network together with all the rest of the data, as well as the rest of the data embedded in Ethernet frames on some layer. In the part of the network that has to recover that network time from PTP, there is a module or a function typically called a clock. And I'm going to use a telecom industry as an example. I'm going to use telecom boundary clock. And this is a diagram from the ITU-T standards. So somewhere from the network, those PTP packets are picked up and transferred to this boundary clock. And the boundary clock processes them, recovers timestamps, recovers timing, and passes that timing information to a time and frequency generator that is sometimes referred to as a PTP server loop that actually recovers a physical time in this module. I'm using an example from telecom boundary clock that supports a physical layer frequency transfer as well. So this portion below down here is basically synchronous Ethernet, and the frequency is traveling on a physical layer of synchronous Ethernet. We can see synchronous Ethernet PLL here that recovers that frequency. And this synchronous Ethernet PLL can be used as a stable clock reference because PTP requires a stable clock for the time recovery. This is a little bit more complicated example and probably not that much relevant to data centers because it would require actual synchronous Ethernet present everywhere. The simpler case is when this time and frequency generator is clocked directly by the oscillator, typically TCXO or maybe even OCXO. It depends on the performance level requirements from the network. So now let's take a look what this little servo is, what it does. So the timestamps are getting extracted from the PTP packets, and there is always a module that basically processes timestamps and calculates the time that is coming from the network. So this is just calculated, not filtered time, as recovered from the PTP packets. Then this local clock has sort of a local clock or counter. The simplest implementation would be just a digital counter that counts time. And of course, there will be a discrepancy between the local clock and the time that is communicated from the network. So how do we compensate? How do we remove that time error? This local time is compared, and this is just pure math usually, is compared with the network time. And then since network time is relatively noisy for various factors, it has to be filtered, usually digital filter, low pass filter. And then based on that, either local clock is running faster or slower, there is a frequency correction that is applied to a local oscillator that is clocking this counter. And the mechanism of this frequency correction can be different. The physical frequency of the actual oscillator can be pulled, or there can be additional digital frequency synthesizer, or just simply counters in FPGA can be adjusted.
Now, can you sorry, can you denote which one of the element is the P8C, the PTP hardware clock? Because
excuse me, which element?
Which one of the elements in your drawing is the PTP hardware clock? Is the P8C?
The output is this one.
The local time. Okay.
So yeah, this is a local time. The physical It can look differently depending on the implementation. It can be, for example, a 1 PPS physical signal, or if it's a pure software, more of a software implementation, it might be as well just a some sort of a time register inside FPGA, for example.
What determines is which element is being disciplined by the PTP servo stack? So if you said it's the local, then yeah.
Yeah, this local clock is disciplined by the network time, and the local oscillator here is just a frequency reference for this local clock, because it has to accept some sort of physical frequency for the counters to operate.
Right. Okay. Thank you. Sorry.
Yeah, it might be a little bit difficult to explain everything in a very short amount of time. So if there are any questions, we can address them somehow, maybe even offline. I mean, if there are any deep questions later. Okay, so moving on about the local oscillator and why its performance is important for this local clock recovered from the network. Looking into what functions of this servo loop are, there are basically the main function is to filter the network noise, and there might be different sources of the network noise. One of them is packet delay variation. The PTP packets travel through the network, travel through the switches. The network might be not time aware. There are delays, and those delays in packet propagation, they cause a significant actually noise in this PTP timing. So that has to be filtered with the pretty low bandwidth. The other sources are, for example, even the grandmaster. Well, it's not perfect. There is some wonder generated by the grandmaster itself, or through when the PTP packets are going through other boundary clocks. Every node in between is adding. It has noise generation performance. It might be adding some noise. So one of the most important functions of the servo is to filter the network noise. And from that perspective, the lower the bandwidth of this loop, well, the better it is, because the lower my low-pass filter, the better, the more filtering is available to me. But from the point of view of the local oscillator, the lower the bandwidth of this loop filter, the better stability of the oscillator has to be, because the oscillator is disciplined from the network, and any slow variations, they are corrected for slow variations of the local oscillator frequency. They are corrected for by the loop. There is a difference here, they are corrected. But if the local oscillator is, if the variations in the local oscillator are faster, the loop bandwidth cannot filter them anymore, so they pass directly and distort the performance of the local clock. So this is basically the same as a simple analog PLL model, just a very low bandwidth and not analog, but the concept is exactly the same. So the local oscillator has to be stable in the short term, because this loop has a high pass response for the noise coming from the local oscillator, and as a result, the fast noise from the oscillator is transitioning directly to the clock performance, and then they both are summed with the network noise filtered by the loop filter to produce the end time error of the local oscillator. And I will go a little quickly through this slide. This illustrates the components of the instability of the local oscillator. And one of them, and probably the most important in this discussion, is the temperature sensitivity. Every oscillator has a certain response to a environment temperature variation. And then there is certain profile, like I have here. The temperature of the environment can change, can vary. There are cooling elements inside the switch box. air conditioning, different other factors. So the temperature of the environment is varying, and because oscillator has certain sensitivity to it, it modulates the oscillator frequency as is shown here at the bottom. And there is also the intrinsic wonder of the oscillator, and less important here because it's a very slow process is the daily aging. So all those instabilities cause certain frequency error in time of the local oscillator that has to be integrated and passed through this high-pass model of the servo loop to end up with the time error contribution of the local oscillator to PTP time error. So basically what that means, this is the model that we use to simulate how much time error is added to our PTP clock because of the instabilities of the local oscillator. And again, I'm probably going to go through those couple of slides very quickly. It's much easier to look at them offline. Those are a few illustrations of the results of the simulation based on the previous model. They show that the better sensitivity of the lower sensitivity of oscillator to temperature variations, typically expressed in ppb per degree C, so how much the frequency oscillator deviates per 1 degree C of external temperature variation. And this is 10x difference between two different oscillators, and we can see that in response to the same environmental temperature variation for a very slow loop of with a 10-minute time constant, those would be the differences between 1.5 and 15 microseconds. And the next slide illustrates if we take the same two clocks but reduce the time constant of the loop by 10x, well, of course you will get less network noise filtering, but the contribution of the oscillators scales proportionally. So we are now both of the oscillators from the previous case and same temperature variation are down to less than 0.5 microsecond. So for the closed loop PTP, what is called frequency slope of the oscillator, which is its sensitivity to temperature variation, how much the oscillator frequency changes in response to 1 degree C in environment temperature change. That would be defining how much disturbance is generated by the environment temperature, and that can skew the performance significantly, as we've seen from those two previous slides. This was just, I'm going to skip this. This was just a comparison of different oscillators. And here is the point that actually was made even before my presentation. So this frequency slope is basically something that has to be taken into account when we are simulating the oscillator impact on PTP, even in front of traditionally accepted frequency stability. Because frequency stability only tells us, well, I have my limits, plus minus 100 ppb, for example, whether my oscillator fits into those limits over temperature or not. But it does not specify how much my frequency changes into response in response to a small temperature variations. And that's primarily the region where we operate, because the loop is closed, we are operating quickly. So in that sense, a clock with a looser frequency stability, but less slope can in fact satisfy the better accuracy of the recovered time. And yeah, I think I'm going to pass on to Gary at this point, and I will be happy to answer questions if you have any time left.
The one thing I want to add is, like, because we reached already 12 So I'm wondering if it's possible to have like basically the second part of your presentation, let's say next in 2 weeks. Like, is that possible, Gary?
Yeah,
Because
absolutely.
I really want to make justice to the topic. Like, it's really a wonderful topic, and I make especially with like the temperature profiles that we have in DC. Like, it would be great. Like, let's say, I don't know, have Nazareth, Gary, like more time to discuss these things with everyone else. Would that be a good suggestion?
Yeah, that'd be great.
Yeah,
Okay.
of course. As you probably noticed, I was rushing quite a bit because it's a lot of material for tomorrow.
And I'm like, I really want to do justice to the topic. I want to give you more time. How about this? Like next week, basically, we have Michelle presenting the PTP profile. We can have you guys first, let's say, continue this presentation, and then we have Michelle's profile, DC profile. Is that good?
That's great.
Mm-hmm.
Wonderful.
Of course. Thank you.
Wonderful. Let's do that then.
I second everything that Ahmed said. This is really great stuff.
You're welcome.
Yes, yes.
Thank you, Datan.
Yeah.
Okay, wonderful. So I wish everyone great rest of the week. And Archana, is there anything else you want to add?
Just that the links that were presented in the chat, if either Kelvin or Elad or somebody can post them on the wiki, I think they're going to be great resources for folks that listen to the call recording if they're not able to attend. So that's my only ask.
Sure.
And then another small point, we do seek for more collaboration and people to come up and join us. So if those things are interest you and you want to make an influence, we really need you to make an impact.
Yeah, if
Sorry,
I was gonna say, if anyone wants to forward the link to the mailing list or to the project page, you can get to the Time Appliances project page from the opencompute.org website under projects, and you can forward that link on to anyone that is interested in joining and hearing more about it in your circle. It's completely open, like Ahmed said. We're completely transparent, so there's no passwords or anything required.
And Hisham, would you please also share like a link or whatever document it was like you were mentioning?
No, I think he did in the chat. I saved in the notes.
Wonderful.
Yeah.
I put them on the chat. Somebody can just cut and paste or put them in the website.
Wonderful.
Yeah.
Wonderful. Thank you, Hisham.
And then the presentations that were made today, if they weren't already submitted to either Kelvin or Ahmed or Elad, if you wouldn't mind, please going ahead and forwarding it to them, and then we can add them as references to this recording in case someone wants to have further questions or reflect back on them.
Sure, absolutely, we'll do that.
If I would like to make a presentation, I have to coordinate this with Ahmed and Michelle, or what's the process?
Hisham, just send it to Kelvin, and we'll put you up right away in the queue, and we'll love to hear from you, from everyone here, including you, everyone else.
Yeah, thanks, Hisham. Yeah.
One last thing, we do have our OCP Tech Week coming up in November. And the TAP project here does have an engineering workshop track. So as you guys start thinking about the work streams between now and the November timeframe, please work with Ahmed, Elad, Michelle, and Kelvin and see what we can do there. We would love to, get some culmination to all of this great conversation and these great concepts that are coming forward. So just keep that in mind as a broader presentation date, the week of November 9th. That's all I had. Thanks, Ahmed.
Well, thank you. Okay, yeah. So let's say bye to everyone.
All right.
Bye,
Take
everyone.
care.
Thanks, everyone.
Bye.
Take care.
Bye.